Hello, my name is Drew Marty Carina. I'm the agricultural modeling scientist here at aWhere. My job entails building predictive statistical models to provide insights for agriculture. aWhere is all about solving problems. That we recognize that farmers today, whether they're big, large-scale industrial farmers or small-scale subsistence farmers, are all facing problems. These problems are due to climate change, due to the need for ever-increasing yields, due to changing pests and disease pressures. It is our understanding and belief that through the power of statistics combined with high-quality data analysis, that we can develop tools that help make the farmers' lives easier. The tools we've developed to date have involved things such as predicting when diseases are going to break out, when pests are going to break out, when crops are going to be ready for harvest, determining where and when the conditions are conducive to certain events. We can do this on a small regional, local scale or large regional scales, and even we're learning more and more how to scale these up to a continent-wide basis. All of this information is meant to be useful to help farmers make decisions. And what I'm going to talk to you today is a bit about the philosophy of the process that we employ, as well as walk you through an example case study of how you might combine a number of different statistical data, models and data together to provide a unique insight. So, to me, modeling is a synonym for statistical inference about a system. When we build a model, we're trying to understand how things relate to each other. These might be things that are expressed in columns of your data matrix. These might be things that you see in the world around you, and you hypothesize there's a relationship between them. The statistical inference is the act of drawing a conclusion. And importantly, we're trying to understand a system. Everything in the world is interconnected. And the process of building a statistical model is about isolating a part of the world that you feel is relevant and of interest to the question you're trying to solve, and figuring out how to describe the interrelationships amongst things in a way that not only explains the data that you use for building the model, but also can be used down the road to explain new data that the model's never seen before. So, what is the process of this model building? Well, to me, there's three main parts of it: data analysis, understanding of probability, and then the statistical inference. Data analysis is the act of gathering, displaying the data, of becoming familiar with the data at the heart of it. That, regardless of whether you're talking about a small data set, maybe a couple hundred rows, a few unique attributes, or a mind-boggling large one, millions upon millions of rows, hundreds of unique attributes, the process is the same in the two in terms of trying to understand it. It's important that you understand the basic relationships amongst your columns. What things are correlating, what things aren't. What is the mean values? Do you have missing data? All of these things are incredibly important for building a sound statistical model because they will affect the final quality of the results. If you see a general pattern in your data except for this one unique case or one unique, a part of certain attribute, it might be worthwhile to investigate that separately. But if you group all the data together, then you might not end up finding anything of interest, but if you divide up your data in an informed way, you might, even though you have two models, they might be very informative each in their own right. All of the act of doing data analysis is a necessary precursor to everything comes afterwards. And it's something that people often view as a chore in order to get to the meat and potatoes of it. But in reality, the heart of any statistical model, statistical inference, comes from high-quality data gathering, analysis, cleaning, and understanding. The second important step is one of probability. It's important to realize that when you build any kind of statistical model, you can never say what the truth is. You can say something is highly, highly likely to occur. You might be 99.999% sure, but that's different from saying 100%. That just the nature of the beast is that you can never be 100% sure when you start talking about statistics until the event actually happens. And so it's important to always have an understanding of probability whenever you go into the act of building a model, if for no other reason that you need to understand what is the baseline that you should compare against. A model that's 50% predictive doesn't sound all that great until you realize that, well, maybe without using the model, you're only going to be accurate 10% of the time. Then that seems like a huge improvement. It's important that you can always establish a baseline for any model so that you know when you're actually succeeding in pulling information out of the system and using it to make a informed prediction that's actually useful for saying down the road. Finally, statistical inference. This is the act of drawing a conclusion from the data and the model that you derive from it. This is at the heart of what we do. And it's important to realize that statistical inference is a creative process. There is not a right and a wrong way to build a model. That there are certain requirements of the data, and that it's important to have stationarity. It's important to make sure that there's not like your columns are overly correlated and whatnot. But in terms of how you actually end up formulating the model, this is truly a creative process, and one that requires you to think both very concretely as well as abstractly as to how the world might be related to each other, how different attributes might work together to drive whatever process you're hoping to better understand. So, why do model? Well, to me, there's a number of important things. The most important one, though, is you can understand the way the world may be. We all interact with the world in our own ways. We all have our own lives. We all have our own experiences. And we all have an understanding of certain aspects of the world. And some of those understandings might be true, some of them might be false. And statistics and statistical modeling is a way to bore down and to understand in more detail how might the world be. We might have a belief that certain some aspect drives something we see in the world, but we could be wrong about that. But by building a statistical model to study it and bringing in all kinds of data, we can start to have a better understanding of which factors actually drive something to occur and which things are more opaque, not connected together. Related to that, the first point is about understanding the different ways the world may be. The second is then assigning a likelihood to the likelihood of each of those things being true. If we're trying to understand model global warming, global climate change, most people believe that the world is increasing in temperature, but how much it's increasing in the rate is more up for debate. And so, but by building a statistical model that incorporates all of the available data, we can essentially assert confidence bounds, essentially assert a relative certainty about one scenario playing out relative to another. This is important because it helps you to prepare for the world. That if something is more likely to occur than another outcome, you're more likely to prepare for it. But at the same time, if something it's very likely or unlikely to occur, but could be terribly damaging if it were to, you might spend the time to prepare for it just in the event that if it were to occur, you're not going to be completely upriver, downriver. And so it's important to understand that there's a lot of different reasons to build a statistical model. Another point for this is it helps you understand how the change in the world affects everything else. The world we live in is interconnected. An increasingly warming world affects everything on the planet. It affects the rate plants grow. It's going to affect animal health. It's going to affect humans. And it's not necessarily clear how all those things will play out. But by building a model that starts to explain it, we can begin to clarify our understanding. There will, of course, be limitations to this approach, but is it better than the alternative of just throwing your hands up in the air and guessing? I would argue yes. Others might disagree. I think there's a lot of power in this approach, but it has to be. It's an approach that has to be done with clarity and foresight and rigor to make sure that you do it well. But at the same time, if you discover a result, you can show someone very clearly how you came up with it, and it opens up a dialogue for my perspective on the world versus someone else's. Furthermore, modeling is really cost effective. That there's lots and lots of data out there, and whether it's you collect it yourself, someone else does, that you can often draw upon it to bring into your analysis. And your analysis can cover anything you might be interested in. In my professional life, that I build these system models, but I also do this in my personal life. I've asked questions for my own, my own house about, how would, changing land use patterns upstream affect the potential for flood. I've been curious when helping, my friends with business plans of, what is a likely market to target that would be successful for their personal product. There's a lot of power in statistics, and it all comes down to how you apply it. And because that, the data is often cheap and computers are so powerful today, it can be a very cost-effective way to begin to answer some of these questions. The final important point to note here is there's a lot of power in statistics, but that you can never discover truth with them. You can only discover what's most likely to be correct. The world is very, very complicated, and the most complex statistical models probably leave out some important detail. And so we can hypothesize to great certainty how the world's going to play out, but you can never be completely sure until you see it actually happen. One point I'm going to drive home again and again in this talk is that the final quality of a model is only as good as the data that goes into it. That you can play around with numbers all you want, but if they don't reflect reality, incorporating them into a model isn't going to do you any good. Models are meant to reveal patterns and truth about the world. A model is expressing the relationship between different things. And if the data that goes into that model doesn't reflect reality, the model's output isn't going to reflect reality either. And so as far as problems with modeling, that's by far, in my personal opinion, the biggest one. There's a lot of bad statistical models out there, not necessarily because the statistics themselves are bad, but because the data that was used to generate them isn't believable. That, when you actually go to review how the data was collected or derived, you realize that there's systematic reasons to not believe the results. And especially if you have the opportunity to compare them against reality, you'll see that the output of these models isn't always consistent with what one would expect. Another point, and this goes back to what I was saying before about you can never reveal truth with statistical models, only high certainty. In order to model something, you almost always have to simplify it. The world we live in, as I'll say time and time again, is very complicated. As hard as you might try to express all the nuances saying mathematically, when it gets down to it, you're going to leave out some detail. If we're talking about agriculture here, you might leave out aspects of physiology, of interactions with weeds, of the fact that, whatever effect you might be interested in might be mediated by water availability or nutrient availability. All of these things are important, but if they're not within the scope of what you're trying to understand, or if you don't realize that they should be included, you may omit it. This isn't directly a problem, but it's always something to be aware of, is that you have to choose when you develop a statistical model a level of nuance that reflects all the important things that you know about the world for whatever problem you're trying to solve, but is simple enough to be tractable. Simple enough can be with regards to either the amount of data you have available, with regards to how long it'll take your computer to fit the model. Each of these is a case-by-case basis, but it's important to realize that you can never express all of the nuance of a problem in terms of your statistical modeling, but you might be able to express enough of it to still derive an informative answer. Another point, correlation in a statistical model does not necessarily mean equal causation. What I mean by this is, let's say you develop a statistical model and you show that you can accurately predict something about the planet. That very well might be true, but you cannot assume that the things that are going into your model are actually what drive the process around. You may have left out some detail that actually ends up being more important than anything else. That detail might actually drive your predictive variables. But you cannot know for sure without additional testing through controlled experiments. And so while statistical models are incredibly informative and useful, You cannot use them to determine causality unless they're paired with a controlled experiment. This is just the nature of science and data analysis in general. I don't view this as a philosophical limitation, others do, but at the same time, it's important to realize that this is true because it's going to inform you how to progressively make more and more detailed, nuanced models as you become more adept at this process. You know, this is this aspect of correlation not equaling causation is something we see time and time again in our culture and society. That this is something that, you know, statistics are often quoted, but without little understanding by those that are citing them as to what the results actually mean. And so you end up being able to derive, you know, or people hypothesizing conclusions that are just not warranted from what's going into what data and models are saying. And so, you know, once again, this is not truly a limitation in terms of what you can do with the modeling. It's just something to be aware of in terms of how you integrate what these models tell you with something else, with what else you know about the plant, what else you know to be true of the overall system. So what can we model? Really is anything that has consistent relationships over time. As I said before, modeling is all about describing the relationships between different things. As I said, modeling is statistical inference about a system. And a system, by definition, has a number of moving parts. And those parts move or work together to create some type of outcome. The problem is that if those parts, if the relationship to those parts is changing over time, your model is going to have to change with it in order to continue to produce accurate results. And you're going to have to build that change into your statistical modeling. And you can very quickly see how this becomes very complicated. And so, you know, in a certain sense, that you need to have consistent relationships over time to be able to build a statistical model that actually ends up being able to predict data outcomes from data that it wasn't ever trained with. You know, what's normally referred to as out-of-sample validation. You know, statistical modeling also doesn't have to be nearly as complex as I think it'll make out to be. Really, any type of, you know, statistical testing and you know, inference is a statistical model. It may be a simple one, but it's nonetheless. So a t-test, I mean, in my mind, a statistical model. Chi-square test, statistical model. That all of them are essentially making certain assumptions about reality and comparing those, using those assumptions to compare data against something on the planet. It might be another set of data. It might be what, you know, what will be determined, like considered like completely random. But all of these things fit into a framework of statistical modeling. To get to a specific subject matter, agriculture is prime real estate for statistical modeling. That agriculture, and more specifically the growth of plants, is largely deterministic. In a greenhouse and controlled settings, you can amazingly accurately predict the growth of a plant based on things like, you know, the ambient temperature, relative humidity, nutrient status. All of these things are important, but they combine together in a highly deterministic way to, you know, to cause that plant to grow at specific rates and specific patterns, etc. Some plants eat more consistently than others. Some plants need other aspects. Length of daylight is a common one. Soybeans is a great example of a crop that requires that. But importantly, that agriculture is a ripe area for statistics. In fact, the field of statistics was developed through agricultural experiments. And so, you know, as far as like specific areas that I'm going to be talking about in agriculture, you know, variety trials, essentially determining, you know, what kind of cultivar or what crop grows best in one area over another. These are, you know, this comes down to building a statistical model to understand it. Plant growth. You know, as I said, plants are, in a certain sense, highly deterministic. Where it gets complicated is when you start having a bunch of plants growing in close proximity to one another. How does that proximity affect things? How does the presence of pests, of weeds, you know, in a certain sense deterministic, but deterministic doesn't mean simple. And so, you know, we can model to a certain degree, the growth rate of plants through what's called either a heat unit or growing degree days, which is also called GDD approach. I'll talk a little bit more so what I mean by this, but it's something that we often use here at aWhere in order to track the progress of a crop in real time. That this could be important because crops are more susceptible to pests at a certain stage of life. They might need different amounts of nutrients. And so it's something that it's information that you can use to refine your other predictions to a much greater degree. Soil moisture is another great one. This is actually very straightforward to represent, and it's something that's critically important for crops. And you'll see how just these three topics can be combined together into a single statistical model to answer a important question. But I'll say it once and I'll say it again. Modeling is combining together different statistics into one story. That a model is a bunch of moving parts fitted together. And what this is all about, this being the act of building a model, is seeing if you can determine how best to fit those parts together to understand how the system as a whole works in order to make a prediction. Those predictions are meant to be informative and to help someone better run their farm, to make an investment decision, to solve some kind of engineering problem. That we do statistics because it's useful. And the usefulness comes from representing how different things combine together to produce a single outcome. So that was somewhat of an abstract talk about it. It's almost philosophical in terms of what statistics can do. So in order to drive the point home, I want to get into an example of a project that we ourselves at aWhere have worked on that combines a number of statistics, a number of different data sets together to create something useful. Essentially, the questions we had is, can we use field variety trials to adapt growing degree day models to a local cultivar? These growing degree day models are developed for a specific crop, a specific cultivar at a specific place. And so you can't necessarily just pick one up and use it on another place on the planet. Most GDD models come from out of the USA. It's just historical fact as to why. But that doesn't mean they're not useful in other places in the world. And so we're going to show you an example of how you might take field data from Uganda, in this particular example, and use that to adjust a USA GDD model to make it useful for an African context. Second, our question is, can we use that locally adapted GDD model and then aWhere's excellent quality global weather data to predict whether a crop is water stressed? That essentially plants use different amounts of water at different stages of their growth. And so it's important to be able to track the growth rate of the plant in real time in order to understand how much water it needs to have available to not be stressed. This is important for such things as predicting the final yield, predicting when it's going to flower. A lot of these aspects are driven by water availability. And so this type of research question has direct utility for many people across the planet. And then finally, can we combine this methodology and apply it on a large scale? It's one thing to apply this model to a single field, but what if we want to do it at a state level, a country level, even a continent level? Is the approach scalable? Can we pull out enough unique information that's nuanced enough that we can actually understand how not just a specific field of maize is doing, but how an entire country's worth of maize fields is doing? As far as the specifics, so the data we'll be using is a variety trial for a variety of maize called Statistical, which is local to Uganda. The maize GDD models we're going to use comes from the United States. Most of these models came out of research in the Midwest, Iowa, Illinois, that part of the country. And we're going to be combining this with what's the model that's used by the United Nations Food and Agriculture Organization for predicting water needs. That if you're not familiar with this paper, this is FAO 56. Highly recommend that you look it up. That this modeling approach is used extensively in agriculture today. If you've ever heard the term crop coefficient, this is where it was derived from. But the core idea here is that you're able to represent how much water a plant needs on an ongoing basis as a function of its growth cycle. As just getting a little more into how that model works, essentially the core idea is that the soil underneath the plant is essentially a cube, and it acts like a sponge where it has a certain amount of pore space available to hold water. And the different textures of soil, so sandy, clay, silt, that they all have different potentials for holding water. Sand can hold the most because there's the most pore space, clay the least because it's the smallest particles and they compact together. That, as I said before, plants use different amounts of water at different stages of growth. And so therefore, what this model essentially is about is determining how much water is going to be used by the plant on any given day, not just based on its growth rate, but also the ambient conditions. Such things as the wind speed, the relative humidity, all of these affect the rate at which the plant photosynthesizes, which is what drives its water usage. And so this FAO36 model is essentially a way to incorporate all this information together and derive a single value that's uniquely informative for answering this question. Furthermore, some water evaporates from the soil. So you lose water in two ways. Plants take it up for photosynthesis, and it also evaporates due to heat. The relative percentage of those two things changes as a function of time. As the plants grow and shade more of the soil, evaporation as a percentage term goes down. And so, what this model further takes into account is not just how much water is used by the plants, but also how much water is available in this actual soil structure. That it incorporates aspects of how does that water replenish into the soil? Where does it come from? Precipitation, irrigation, how much of it can stick around? What is the rate at which it can infiltrate in? And so all of these things are combined together into a single model that allows us to, as I said again, drive a single value so that you can compare how maize at one stage of life uses water relative to another, or how different crops use water relative to one another. Like whether if you're expecting dry conditions, maybe it might be better to plant sorghum than maize because sorghum is more drought tolerant. This model allows things to be compared on equal footing. Is the model perfect? No. But is it accurate enough that it's useful? Absolutely. Getting into data. So here are the GDD models that were derived out of the U.S. So as in the U.S. and everywhere, as just as everywhere else, there's different varieties of corn that differ in terms of how much of the season they need to grow. We have short varieties. We have long season varieties, and we have intermediate ones. That in this particular case, with the data, with the model, like the variety of corn that we're studying from Uganda, it corresponds to an extra long season crop. But at the same time, is it perfect? No. And should you just use the closest GDD model to it? Probably not. And so, by essentially taking a more nuanced approach and looking at all four of the models and maybe using the information together, can we, more readily adapt the data for, the variety that we have of a unique cultivar to the information that's available in literature to drive some type of informed outcome. This is broken down by growth stage. So for those who aren't familiar, maize has a number of distinct stages. It can be divided into two growth stages, vegetative and reproductive. During the vegetative stage, the different growth stages are defined by the number of leaves. The reproductive stages is defined by the growth rate of what is going to end up being the corn cobs. That's what is determines the final yield. And so you have things like V2, V8, which corresponds to 2 and 8 leaves respectively. You have the tasseling stage, which is the transition between the two. Silking, dent, all of these things are, if I tell you what stage, you should expect the plant to look a specific way. As you can see that, we have 4 different lengths of the season here, and that these correspond to the number of accumulated growing degree days that are necessary for the plant to reach each of these stages. In terms of for the Sika variety, so the data that we had from the variety trial only had the planting and harvest date. And so, we know the full length of the season, but the question is, okay, so when do all these relative stages occur? Because, the water usage is going to start increasing as these stages progress. And at a certain point during the vegetation, at the reproductive stage, it's actually going to start declining again because the plant's maturing. And so the thing is that, we didn't have all the data we want to. Does that mean we can't do this project? No, it just means you have to get a little more creative about how to do it. And so what we did is that we calculated the number of growing degree days between the planting and harvesting date, and then used that information to scale the average of those other GDD models in order to drive when that these different stages probably occurred. Is it a perfect approach? No. But is it accurate enough that we can provide useful insight to farmers that might be trying to handle their irrigation or determine whether this is a available variety or a valid variety for them to grow given what they expect their water supply to be? Absolutely. And so, I make the point again, you don't have to have perfect quality data to make a model, but you do have to have consistent data and a creative mind for how you might combine things together. Because of the way that this FAO56 model works, we don't need to know all of those stages separately. We only need to know the major ones. And those can be simplified down into these 4 points in time. Essentially the initial stage, which is when, which is post-emergence and is when the plant starts putting out leaves. The development stage, which is, later on in the leaf and right when it's starting to enter flowering. Mid is during the main part of the reproductive development when the corn cobs are most fully forming. And then final essentially is physiological maturation. This is when the plant starts drying out and begins to be ready for harvest. These correspond to what the FAO56 model delineates as when there's changes in the available water usage. And so to simplify this, we condensed the previous GV model that's specifically for Statistical into these stages because this is the information we need to carry forward and use that water model to feed into everything else. This is when you take that data, that this is essentially the information you drive out of it using the model. One point to note is that accompanying this talk is the case study that we actually show you the code used to derive these things, the data sets that we use to do it. And so while I'm not going to get into the specific coding here, that you will be able to play around with all this information and see, maybe you felt that we made an assumption we should have. Maybe you wonder, what if it had been this amount of water usage for something else? You'll have the power to investigate that. As I said before, the FAO56 model boils down to deriving a single value for the available water usage as a function of growth stage. Lower values on the y-axis mean less water use, higher values mean more. And so each of these kinks in here represents, initial, mid, development, physiological maturation. And this is essentially showing that as a function of time since planting, the plant uses different amounts of water. This is the standard one for maize. This is not, taking into account specifically for Statistical. However, when you adjust it based on some of our assumptions about this variety relative to standard maize, both in terms of length of season as well as in terms of the fact that it's like a drought-tolerant variety, that's what it was specifically bred for. Furthermore, it's grown at smaller densities, like planting densities than standard maize, and so it's going to use less water. And so you can see that using this information, we can actually scale our, what a standard maize plant would use and adapt it for, based on all of the best available data we have, how much the Statistical variety actually would use as a function of its growth cycle. Furthermore, that what we're now using this information for is we're what we did is we pulled our weather data for a specific site that this variety is being grown. And this is showing how much water is available in the soil profile as a function of the planting, of the days since planting. That the y-axis represents the total available water. A 1 represents that the soil is fully saturated and has much water as it can hold. 0 means it's bone dry. There's no water for the plant to take up. The red dots indicate the days it rained. And so you can see that on the days it rained, that the amount of water in the soil profile increases. That the amount that increases is determined by the total amount of rains, whether it rained fast enough that some of it ran off, how much water the soil can actually hold, and a number of other factors. But you can see that, looking at this data, there was a period where this corn was subjected to an intense dry spell. And so, if you're growing a different variety, maybe the water wouldn't have run out as quickly. Maybe this is saying at that location, you need to grow something that's even more drought tolerant than this variety. On the other hand, if you showed that there had been no stress during time, maybe it might be better to grow a higher yielding variety, but that might be more susceptible to drought if it were to occur. That this information directly doesn't tell you, it's not a yes or no answer, but it allows you to inform yourself as to the best way of making your decisions for next year. Should you grow this variety again? Does this make sense to fit into your overall cropping system? That by combining together these different sources of information, you can derive information like this that you're able to look at and say, okay, this will help me as a farmer to decide how I'm going to approach my operation from this point on. And I don't mean to emphasize that this is the only type of information you can derive. It's just the one that we decide to focus on for our specific purposes. Now, furthermore, you have to ask, why did we do this? Now, I understand this is a variety and I'm talking about this as a variety adapted to Uganda, and I'm showing you a map of India now. But, what I thought would be most beneficial is to make a point is, this is actually a figure that I developed for a client, where we're taking this exact model and saying, okay, we're not talking about Uganda anymore, we're talking about India, and we're not talking about corn, we're talking about cotton, but it's doing the exact same thing. What each of these dots is showing is the places where the plant either experienced no water stress, about average water stress, or extreme drought conditions. That, all the places coded red are places that the crop had incurred strong drought. And you expect that those places, the crop is not going to have done well. Alternatively, all the places green, probably doing very well. Yellow, more in the middle ground, probably going to do about what it does on average. But the point being is that you can take a model that was developed for a specific field, for a specific cultivar, and through an understanding of both the statistics, the agronomics, the socioeconomic demographics, you can systematically scale up and produce insight like this that is uniquely informative. Are we going to be right every single time? No. Are we right on average? Absolutely. Is this something that a county plan or a state planning department, a national government, some type of regional entity could use? Absolutely. That this is the power of statistics. It's the ability to scale, the ability to understand not necessarily how any one thing is in certainty, but how a huge number of things are on average. As I say again, statistics is not about truth. It's about likelihood and certainty. And it's this type of information that you're able to derive by the systematic application of data, of modeling, of agronomic intelligence, of understanding of biology. All of these things combined together to be able to produce insight like this, which is what aWhere specializes in doing. So in total, to me, statistical modeling is a powerful way to study the world. You need high quality data to do it, and you need to make assumptions about the world to simplify it to enough that you can model. But that there's power in that. that by simplifying, you're able to focus on the details that matter and omit the ones that don't. And by doing so, you're able to increase your power to detect nuanced changes. Is there always a concern that you might toss out like information that was actually important? Sure, but this is where doing things in an informed way that's not just relying on straight correlations, but also an understanding of biology, physics, agriculture. All of these things come together. And so this is why I say time and time again, modeling is a creative process. That there is no right and wrong way to approach something as long as that you're consistent and you fulfill the requirements of the techniques. And so with that, I would like to say thank you, everyone, and goodbye. You're good.